Your audio. Hey, we've got Ashley already. We've got a student. Let's see if I can get this to show up here. How come I'm in the shadows here? Oh, gee, I think I need to turn off some of these lights. That's just ridiculous. Is that gonna? That's a little better. Okay, maybe I need to adjust this just a tad. Let's see. Yeah, that's pretty good. Okay. All right, well, let's see who we've got on board here. Oh, we've got Brendan and we have Ashley. How are you guys doing this rainy morning?
Oh, I'm good. How are you? I like the rain,
Where you
but
are, it's raining here. I'm kind of in the middle of town.
my puppy does not like the rain as much.
Let's calling Brendan and Ashley. Come in, Brendan or Ashley. Say hello.
Can you hear me? Hello?
They're not going to answer me.
I can hear Brendan.
Yeah. I think you might be muted or your audio isn't on, bro.
I wonder if I needed to adjust that just a tad. That's pretty good.
I think his audio is off.
Well, class hasn't started yet. We have 3 minutes, but you've got 3 minutes if anybody wants to ask me a question. Oh, there's Darren. Darren, unmute and say hello.
Hello? Professor? Hello? Oh, no.
Your sound is off.
Allow participants to unmute themselves. We've got Darren, Brendan, and
Hello?
Ashley so far. Okay, that's good.
Hello, hello. Yeah, his stuff is off.
Well, today's Thursday. And there's Ben. Ben's here. Good deal. Ben, unmute and say hello. I need to see if you guys are hearing me here.
Good morning.
See the board.
I don't think you can hear us. We've been trying to say hey.
Nobody's going to answer me. Well, I was
Oh,
looking
man.
at your homework there. I'm trying to get it graded. I'm a little behind, but I'll get all your homework graded. But there's one due tomorrow night at midnight. Let me write that down. Homework number 7, which is problem 226 on page 82 is due tomorrow, Friday at midnight. And now homework number 8 and that's problem 229 on on page 82. It's on the same page. It's due Sunday night at midnight. So get your homework, do your homework there. Okay, let's see who we got here. We got Braxton, Ben, Ashley, Alex. Got a good class here. We have Shane and Mohammed and Darren. Somebody out there say hello.
Professor, can you still hear us, or?
I need to see if I got anybody who's actually really there. So say hello.
Hello, Mr.
Hello.
Griffith.
From Darren Turner to me, I can hear you and each other. Good. That's good. That was a chat, I guess. Good for you. You can't hear us, though. I wonder why I can't hear you. Let me see. Maybe there's a.
I think he just muted himself.
Yeah. I think once he figures out that he's got to connect to the audio, I don't know.
Okay.
'Cause, like, every time you come in,
You suppose that?
Mhm.
like,
Can you hear us now?
Me? Earth calling students.
yo, Vince.
From Darren, we can hear you. Can you hear us? No, I haven't heard. I can't hear you.
Oh,
Darren, can you hear us? I can't hear you guys. You have to unmute yourself.
yeah. Mm.
Hey, Mohammed, can you hear me?
Yes, sir, I can
Darren,
hear
Shane,
you.
Anybody? I want to find out if we're working here.
Sir, I can hear you.
Ashley, Ben,
I don't think he has no idea right now what to do.
Yeah, he definitely
Brendan.
can't hear us.
Should I create like a
I'm gonna
note?
do my
to put on
class. We'll have a lot of fun here, but there's a thing down here that says mute. Mute my audio. I want to unmute. You are muted. I am muted. The heck? Oh, I'm so sorry to waste your valuable time doing this, students, but we've got to get connected here, don't we? There is a thing that says mute. Mute my audio. Alternate A. Do I want to push alternate A again? I already pushed it once. Alternate A, okay. Did. Now you are muted, Brendan says. We haven't had this trouble before. From Brendan to everyone, now you are muted. Okay. It says recording, unpinned video. I don't want to do that. Talking. This says mute all. Mute all current and new participants. How about now? Can you guys hear me now?
Yep, I can
Yeah,
hear
we
you.
can hear you.
Testing 1, 2, 3, 4, 5, 6. We're trying to get connected here. And I hate this. Maybe I should call my IT person. Nobody's answering me. Let me get my cell phone and call my IT person. I'll be back. Okay, I'm trying to call my automatic voice message system. Okay. Hey, IT person, I am I'm getting video here, but nobody answers me. And somebody send me a chat and see if you can hear me. Can you do that, please? From Darren Turner to everyone. Yes, we can hear you. From Samuel. Samuel says we can, but I can't hear them. They can hear me. They can see the board. I guess I'll go ahead and do my lecture because they can hear me and they can see the board. But I would like to hear them. Yep, we can hear you, Brendan says. Thank you so much for responding. But why can't I hear them? Well, anyway, please call me. Okay. Maybe she'll call me back here in a minute. All right, well, as long as you can hear me and I got the board here, I'll go ahead and do what I wanted to do. There's some homework that you can do for me. Let's do review problem 1.6 while I'm waiting for my IT person. Go in your book and help me find. We're just going to go over stuff from chapters 1 and 2 here to make sure that we know how to do it. There is a test next week. It's a take-home test, open book. You'll do fine. But this review problem, I'll tell you where it is. It's on page 67. Always before I was able to talk to you guys. So why can't I talk to you now? It's bugging me. Okay, now if you look at this problem on page 67, it sure looks like to me, it looks like a round tank. Doesn't it? The way they've shaded it and everything. But you know what? That's deceptive. If you read it, it's square on the bottom. So it's not like that. It's like this. Part of the problem is trying to figure out what on earth they're asking in these problems. See, it's really like that. They've got a funny lid here to it. There we go. But it's square on the bottom, and it's 150 millimeters by 150 millimeters, so that'd be 0.15 meters by 0.15 meters. So the area would just be 0.15 meters squared. That's the area. Okay. And then they have a 6 kilonewton force on it. Let's draw that. 6 kilonewtons. But they had a angle here. They made an angle, kind of like that, of it looks like 30 degrees. I think they drew their angle here, but it's the same idea. See, there's 30 degrees. And they wanted to know if you cut this body at that angle, they wanted to know the normal stress and the shear stress. Well, I gave you those equations, and they go like this. The normal stress is that force. It would be the 6 kilonewtons divided by that area. Let me get that area. I ought to be able to do that in my head. You know it? Is it 0.0225? I'm not sure about that. Let me double check it. 0.15 squared. I got that right. And so you divide by the point. Oh, come on now. 225. Can you guys read that? Yeah, maybe. It's not very dark. And I need to write bigger. Let me try my person again here. We'll try again. But see, for the normal stress, you've got to go cosine squared of theta. For the shear stress, hey, my students can hear me and see the board, so I'm going ahead with this lecture, but I can't hear them.
Have you muted them on accident, maybe?
Well, I don't know. I go down here to where it says participants.
Oh, turn up your volume. I turned it down last night.
How do I?
On the like on your keyboard, on the first row, the very first row, there should be a tiny button that it looks like a what's it called? I can't think of the word.
Like a microphone or something? I'm
What's
look.
that called? Like it looks like a speaker.
Looks like a
It
speaker.
should say like plus and minus.
Now it's not on my keyboard. It's on the screen up here, right?
No, it's on your keyboard.
On my keyboard. Is it way up at the top or down at the bottom?
Way up at the top.
Ah, okay. I think I see it. Just a minute now.
There's like a plus sign and a minus sign.
Yeah.
Do you see it?
Push the plus sign.
Push the plus sign and see if it does anything.
Okay, I'm pushing the plus sign. Now somebody say something out there.
Hello.
Hello.
Professor
Hey, I
Griffin.
heard somebody. Say hello
Hey,
again.
there we go. Hello.
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 See,
There we
it
go.
really helps to have an IT person. I think we're okay
I
now.
did that last night. Okay, sorry about that.
Yeah, you're forgiven. Okay, thanks so
All right.
much. Bye-bye.
All right, bye.
See, it really is nice to have an IT person. A personal IT person. Okay, good. Well, now back to what we were doing there. The catch is this theta. Now, this theta is the angle with the well, it's this angle here. Yeah. It's this angle here. Now I lost my page. Just a minute. Let me go back to page 67 here. Yeah, I think getting confused now. It's either 30 or 60, but if you get the wrong one, you get the wrong answers. See, I'm used to, here, let me go ahead and write this. Somebody say something else. Mohammed, say something to me.
Hi, Mr. Griffin.
Yeah, yay, Mohammed's on board. Good deal. Now this one is sine theta, cosine of theta. But you got to get the right angle. Now the way I learned this, we were always doing beams, and we were taking cross sections of beams like that, and the angle that you want is the angle with the perpendicular to your beam. Well, this beam here, it's not a beam, but it's turned sideways. And I have trouble with 3D stuff, but I think it's 30. So we're going to put 30 in here. We're going to put theta is 30, and we're going to go ahead and get our normal and shear stress. If you turned in here late, what we're doing is we're just going over stuff we're supposed to know from chapters 1 and 2. Because I don't want to send you guys off to OSU or wherever you're going and you not know how to do some of these basic things. Okay, I'm going to do this now. Let's go. 6,000 divided by 0.0225 times the cosine of 30 squared. I'm getting 200. I'm getting 200. Now, wait a minute. 200 kilopascals. I think that's what I'm getting. Let me do this one. 6 e to the third divided by 0.0225 times the sine of 30 times the cosine of 30. I'm getting 115.5 kilopascals. Now let's see what the answer book has to say about this. Now this is R16. I'm going to go back here and shop around. And they say R16, the normal stress is 200 kilo. Yay, that's what they said. And the shear stress is 115 kilopascals. Good. So we did that right. And we've got that review problem 1.6 where we understand it. The trick is getting this angle right. And here's how I remember it right here. Any questions on that? I guess you're okay then.
Nope. So I guess the audio works now.
I can hear you. Now, who am I talking to?
Brendan.
Brendan. I wonder, Brendan, if I push this thing again, if it'd be louder. Brendan, say
No, no,
something.
you're perfectly. No,
You
you're
can hear
perfectly fine.
you can hear
Yeah, I
me
can hear you
fine,
fine.
and I can hear you fine. It's working.
Good.
Good. Okay, well, let's try this one now. Let me acquaint you with the gauge, the wire gauges. There, you know about the homework. Maybe I should leave that up there for a little bit more. You know, they have wire gauges. Wire gauges. Now, this isn't in your book. This is extra. We're not going to charge you any more extra money on your tuition for this. This is a freebie. Of course, you could go to Google and you could Google wire gauges and you could get whatever you wanted. But like, for instance, there's a 12 gauge. That's not a shotgun. It's wire, and the diameter. See, a 12 gauge wire. The diameter in inches is 0.0808 inches, and in millimeters it's 2052 millimeters. And they have a 14, 16, 18, 20, etc., gauge wire. Like, for instance, an 18 gauge wire has a diameter of 0.0403 inches and 1.024 millimeters. What's really weird is it's similar to shotguns. You know, a 12 gauge is a much bigger shotgun shell than a 20 gauge. The way it works is the bigger the number, the smaller the diameter of wires. It works that way with shotgun shells too. Okay, interesting. Well, let's string a wire now. So I know I've got my list of wire gauges, and let's suppose you had. You don't need this stuff anymore. You could look that up. However, I think I might have made a mistake on the schedule. At least I wrote it up there for you. Let's suppose you hung out kind of like a clothesline. There we go. Oh, come on now. We're gonna hang something from a clothesline. There we go. Of course, you have your posts over here holding the wire up. And suppose you hung 2 kilograms. You have a 2 kilogram, and we'll have an 18 gauge wire. And the diameter is 1.024 millimeters diameter. And what we want to know is what's the stress? What's the stress in the wire? We could assume it's steel, and we could look up. We're going to learn all about the properties of steel, but we could find out if a steel wire, an 18 gauge steel wire on a clothesline like that, could support 2 kilograms. Now we'll need this angle here. So let's suppose this angle is 5 degrees. How's that? There's a 5-degree angle here. 5 degrees, okay. Now, how would you go about finding the stress in that wire? Let's go to one of my students here and ask them what they think. Let's go to Shane. Shane, unmute and tell me, how would you go about finding the stress in that wire? Do you have any ideas? Unmute and tell me if you have any ideas. Uh-oh, he's not going to answer me. How about Samuel? Samuel, we want the stress in this clothesline wire. How would you get started, Samuel?
Finding the external loads.
Yeah, yay, good going. External loads. Let's do that. Samuel, that is so good. Samuel, what we need here, you stay on the line, Samuel. We're going to use you here. We're going to find this external load. And like Samuel said, we're going to find this tension in the wire here. Of course, it would be the same here. Good going, Samuel. Okay, Samuel, how do you figure this force right here? They call it weight. It's the weight of the 2-kilogram load there. Probably some soggy, wet sweaters out of the washing machine that you're hanging up there.
You multiply it by 9.8. That is the
Yeah,
acceleration of gravity.
Good going, Samuel. So I tell you what we have here. We have 19.62 newtons. Now we need that tension. Now, since Samuel did such a fine job, let's give him the time off there, and we'll go to Julian. Unmute, Julian, and tell me how I'm going to find that tension there. How do I find that tension, Julian?
You'd have to find like the external loads on the wire.
Yeah, that'll work. I think he knows. Julian knows. See what you do here.
Because like the sum of them would be 0, right?
You go the sum of something equals 0. You could go the sum of the forces equals 0, or you could go the sum of the moments is equal to 0. That'd be fine. Well, why don't we do the sum of the forces is 0? That'll work. And let's do them in the y direction. So see, this tension has a y component. It's kind of subtle here. See, it has an x component and a y component. And so what we're going to do is we're going to take the y component. Well, that's t sine of 5 degrees. That's the y component. If nobody understands that, I'll be glad to go through it. It's simple trigonometry. But see, there's 2 of them. So you'd have to add the other t sine of 5 degrees. They're going up, and this is going down, 1962. And they have to add up to 0 because the sum of all the forces in the y direction has to be 0. Hey, there's only one unknown. We can solve for the tension. Okay, I need one of my excellent students. Well, all of you do it. Yeah, all of you do it. And then I'll pick on somebody here in a minute. I'm going to do it. Find the tension there. And take your time, but Jackson, when you get it, report to me what the tension is in that wire. Jackson, how you coming? Are you working
Getting,
on it?
yeah, getting 225.
I didn't get 225. We have an equation here, Jackson. We know everything but the unknown. I know you can solve this.
Oh, hold on.
Maybe I did it wrong. Let
It's
me
half
do
of that.
Huh?
112. Is it 113? Yeah, I got divided by 2.
Jackson, what are you getting this time?
113.
Well, that's not what I got. Let me do mine over again. You're not in radian mode, are you? Because if you
No,
are,
I'm in
it's
degrees.
going to be screwed up.
Yeah, it's in degrees.
You're in degrees? Because we don't want radian mode right now. Jackson, what'd you get what'd you get again?
I got 113.
How on earth did you get 113? See what I did was I went, there's 2 of these, so there's, now maybe I'm wrong, but I'm getting two of these. Equals 1962. And then I'm taking 1962 and I'm dividing by 2 and I'm dividing by the sine of 5 degrees. Oops, you were right all along. I'm proud of you. I think you were right. What did you say you got?
It's 112.55. I tried it up to 113.
Yeah, well, we're going to call it one. You want to call it one? Well, let's call it 112.6. Is that what you were trying to tell me? 112.6?
Yeah.
See, you were right and I was wrong. I was pushing the wrong buttons. Well, we did great. We found that, but that's not what we wanted. We wanted the stress. Now to find the stress, you've got to take that force, the 112.6 newtons, and divide by the area. Well, the area, we never did get the area, did we? Here, let's get the area. The area would be pi over 4 times the diameter. But now, wait a minute. That's in millimeters. You're going to have to go 0.01024 squared. This is how you get the area. Now, if you don't understand that, speak up. I'm going to get the area now. Pi divided by 4 times 0.01024 squared. Well, I'm getting a very small area. I'm getting an area of 8.235 10 to the minus 7 meters squared. Somebody double check me on that. And that, see, you have to divide by the area, which is 8.235 times 10 to the minus 7 meters squared. Now, did anybody get that? I need to hear an uh-huh. Anybody get that?
Yeah.
Yeah. Okay, now solve for the stress. Go for it. Plug that in and let's get the stress now. Here goes. And somebody tell me what they got. Let me ask somebody. How about my friend? Let's see. How about my friend Alex? Alex, unmute and tell me what you got for the stress.
I got 13.67 times 10 to the negative 7.
It's the right numbers, Alex, but it's the wrong exponent.
Ooh.
Do it again. I like the 13.67 that you said, but you got the wrong exponent. Do it again. What'd you get this time?
It's positive 7.
Yeah, that's more like it. I think what you just said is right.
Yeah,
Yeah.
the 13.67 times 10 to the positive 7.
Yeah, there you go. Excellent. I think what I'm going to do is I'm going to write this as 136.7 megapascals. 136.7 megapascals. I think that's the same thing as what you said. You said 13.6 times 10 to the 7th. I think that's the same thing. There's some room here. Let me write it. I believe that was Alex. He said 13.6 times 10 to the 7th. What I'm saying is 136 times 10 to the 6th. See, I made this one smaller, but if you make this one smaller, you got to make this one bigger. So we have 136 megapascals. I need a couple of ahas on that.
Yes.
Yeah, there's one.
Yep.
There's one.
That's what I got.
Great. We just figured out the stress there. Now, I tell you, if it's steel, you can go back in the back of your book and find out if we're in trouble or not. Need a little room here someplace. Here's some room right in here. Now, if you look on this back in the back flap of your book, it says that steel has a yield strength of 250. Now, I haven't explained yield strength yet. 250 megapascals. What that is the stress at which steel yields. It's called the yield strength. But see, we haven't yielded. Look, 136 is smaller than 250, so we're fine. That clothesline is not going to come crashing down. We're okay. Now, if you had a stress bigger than 250, something bad happens, okay? You've exceeded the yield strength of steel and something bad happens, but we're okay. All right, let's do another one. Any questions on that? Okay, well, let's do another one. Here, let me make a little room here. Why don't we do the same thing only in Inglés, señor? Habla inglés? Let's have our clothesline, 18 gauge now. It's still 18 gauge. Only see, 18 gauge in English has a diameter of 0.0403 inches. But we'll have a 5-degree angle there on our clothesline. And here, let's put a 5-pound, we'll put a 5-pound weight on there. We'll hang 5-pound weight on there. Yeah, that'll work. Okay, now I need to know, I forget which wonderful student helped me at the beginning there. but they said get all the external forces. What is this external force right here? Let me go to one of my wonderful students here. Let's see. How about Ben Seaman? Ben, can you hear me? Earth calling Ben Seaman. Come in, Ben Seaman.
I can hear you.
Yay, good deal. Ben, what is this external force of that soggy, heavy sweater that we're going to hang on that clothesline? What is that? What do I put right here for the force?
Would it be just 5 pounds of force?
It would be, Ben, I'm so proud of you because some students, they're confused about that. They multiply by gravity or something. It's not, that's already force. So you don't multiply by gravity. 5 pounds is 5 pounds, Ben, proud of you. Okay, now, do you remember how we found that tension? We had tension sine of 5 degrees going up, but there's another component going up. Tension sine of 5 degrees. And then you're going to subtract 5 pounds equals 0. Okay, I want you to solve for the tension. Go ahead. Not just Ben, everybody. Go ahead, everybody. I'm going to do it. I'm going to try not to goof up this time. So I pushed the wrong button last time. Do it. Find the tension. In English, senor. If you just tuned in, we're going over some of the basic ideas in chapters 1 and 2. This stuff here is from chapter 1. Well, I got an answer. Let's go to my friend Ashley. Ashley, unmute and tell me, what'd you get for the tension, Ashley?
28.68 pounds.
Yay, that's what I got. I got 28.68 pounds. Now we're going to have to get the diameter or the area. Now the area is equal to of a wire, the diameter there is equal to a pi over 4 times the diameter. It's in inches squared. So go ahead and let's get that area. Go for it. Here goes. We're going to find the area now. I got my area. And let me go to one of my wonderful participants here. Braxton, I forget if I've called on you yet. Braxton, I'm calling on you now. I need the area. What'd you get, Braxton, for the area?
I got 0.001276.
What I got?
I don't know how far you want to round it.
I don't know. 1, 2, 7, 6 looks pretty good to me. Okay, now we're going to get the stress in English. See, we did it in the metric or the SI before, but now we're going to do it in English. And so we're going to take 28.68 pounds, and we're going to divide by 0.00127 6 square inches. Braxton, go ahead and do that and tell me what you get. I'm going to do it.
I got 22,476.5.
Okay, now for some reason I got 22,484. I bet one of us rounded off something, don't you think?
Yeah.
I think we're okay though. Now Braxton, what's the units on that?
PSI.
You're right. Now they normally express that in KSI. So the stress, the normal stress, it's this Greek letter sigma, is 22.5 maybe KSI. Now let's go to the back, and if this is a steel wire, we're going to look up the yield strength in English. English, senor. Go to the back, and it says here in the back, need a little room here. Here's some room. They call this the yield strength, and we're going to study it very soon. But they said for this is for A36 steel. It's what's the name of that steel? It's anybody know the name of it? It's what they build stuff out of all the time. Structural. It's structural. This is structural steel, A36 steel, and it has a yield strength of 36 KSI. Hey, I wonder if the 36 KSI has any relationship to the name of this structural steel. What do you think? Yeah, that's it. That's how they got the name. A36 steel has a yield strength of 36 KSI. That's interesting. And now how are we doing? Well, we have 22.5 KSI. Are we in any danger of something bad happening? No, because 22 is smaller than 36. Now, if the stress reaches 36 KSI, something bad happens to our clothesline. But we're not there yet. We're fine. You could hang that 5 pounds of soggy sweaters onto that line and you'll be just fine. Okay, well, that was kind of fun. Any questions or comments so far on anything? Any comments or questions on anything? Well, okay, let's do one in the book. Here we go. I need the room here, so we're going to say goodbye to all that. Now this is problem F113. Help me find it. F113. There it is. It's on page 55. Problem F, that's a fundamental problem. And they've got similar deal to what we've been studying here. It's kind of a sagging clothesline, only it's not a clothesline. And they have a, how heavy is it? Does it say? Let me read this. 200 kilogram. Man, that's pretty heavy. 200 kilogram. That's like 440 pounds. That's like two very strong people hanging there. Yeah, kind of heavy. 200 kilogram. We're going to put 200 kilogram. Now they said this angle here is 60 degrees. 60 degrees on both sides. Okay. Let me read this now. I'm on page 55. We're going over some chapter 1 and chapter 2 fundamentals that we've got to know how to do. We're going to find the stress in these. They're not wires, though. In this case, they're rods. They're metal rods. Now, they said that we must not exceed 150 megapascal. That's your maximum allowable stress. For some reason, they don't want us to exceed that. Okay. Now, how big is, oh yeah, it's 200 kilograms. We know that. And what they want to know is the diameter this time. They want to know the diameter of these rods. Okay. Well, we just did problems like this. First thing we got to do, remember, is to get the external forces. There's going to be tension in these rods. And there's going to be a weight here in newtons. I'm going to shut up here now for a minute and a half or 2 minutes, whatever. And I want you guys to get this in newtons and to find the tension in newtons, and I'll be quiet. I want you to do that. Go for it. Let's see if you can do that. We're after this. Well, we're really after the diameter. They're giving us the stress. We want the diameter. Okay, well, you've had enough time to get that, I think. Let me go to one of my very best students. Shane, unmute and tell me what this is in newtons. What's that for, Shane, in newtons?
Or 3 months then. I got 1960.
Well, that's what I got. Keep going, Shane.
Yeah, I already did.
Now I got 1962, but let's don't fight over it.
I'm gonna inspect that one. Inspect 22 and
make sure 23 is good to go. That way you guys don't have to do them while you're gone.
I think I'm gonna mute everybody, but
I don't know,
you
you guys may have.
can unmute it individually. But Shane, you know what you did? You went 9.8 and I went 9.81, so it's no big deal. You're okay, right, Shane? Unmute Shane and say, uh-huh.
Yeah, I'm good.
Yeah, he's good. Okay, now we're gonna find this tension. Let's go to another wonderful, Samuel. Unmute Samuel and tell me what that tension is.
I got 962 newtons.
Say that again, 962?
Oh, sorry, 1962.
Yeah, I did too. Isn't that weird? You know what I'm getting? I'm getting 1962 newtons here, 1962 newtons here, and 1962 newtons here. Wow. You know why? Let me tell you why. What we have here is we have 120 degrees, 120 degrees, 120 degrees. Does it make sense to you guys that if you have see, there's 120 degrees here, there's 120 degrees here, there's 120 degrees here. Does it make sense to you guys that these tensions would all be the same? It kind of makes sense, doesn't it? Yeah, they're all the same. But if anybody wants me to go through the equation to get that 1962, just speak up. Just say, Mr. Griffin, could you show me that, please?
Yeah, could you do that?
Yeah, I'd love to. Here we go. Here's what you do. Now who was that?
Brendan.
That was who?
Brendan Harvey.
Brendan asked me. Thank you, Brendan. Okay, now here's what you do. You take all the forces in the y and you set them equal to 0. Now you see, this has a little y component. And I'll tell you what it is. It's t sine of, well, what you need is the 30. That might be confusing to you. See, this angle here is 30. See this angle here, that's 30. And to get the y component, you go t sine of 30. But there's two of them. So you go t sine of 30. Then you have to subtract 1962 equals 0. See, the sum of the forces is 0. And when you solve that, you will get 1962. That's how you do it. Brendan, do you understand that now?
Yeah, I do. I was actually doing t sine 60 while I was calculating.
Uh-huh.
You cleared that up.
Yeah, it's tricky. See, you don't want to do that. What you were getting was the horizontal component.
Right.
You wanted the vertical component. Okay, now we're not through yet. We figured out the tension. Now we have to get the, I was going to say we have to get the stress, but see, they're going to give us the stress. They're going to say, let's max this thing out and find the diameter. So here's what you have to do. If this is the stress, which is given, read the problem. It's on page 55. Then what you do is you take that tension, which is 1962 newtons, and you divide by pi over 4, diameter squared. We're going to take this equation now, and we're going to solve for the diameter. Go ahead. I'm going to shut up here for a minute or so, and I want you to find the diameter. And what that's going to be is the minimum diameter. You can have one bigger, but you can't have one smaller because the stress will be too big. Go ahead and solve that, and I'm going to do it and see what I get. Here goes. We're solving this equation for the diameter. Go. Well, I did that. I'll make a little room here. I did that, and I got a diameter. My calculator says the diameter is 4.08 times 10 to the minus 3 meters. If you did it in millimeters, it'd be 4.08 millimeters. Now they wanted the answer to the nearest millimeter. Well, you don't want to round down and have 4 millimeters because the thing would have problems. You want to make it bigger. To the nearest millimeter, you would want your diameter to be 5. Does that make sense to everybody? You see, it's going to be stronger when it's 5 millimeter diameter. Okay, now let's see if that's the answer. Look up F113 back here in the answer book. We'll see what they said. They said F113. They said the answer is 5. That's what they said. Look it up. We did that problem right. Do you have any questions on fundamental problem 113? Here's your chance if you didn't understand it. Okay, well, we're going to do a problem in chapter 2 now, if you're happy with that. We're going over stuff in chapters 1 and 2 to make sure that we know what we're doing. Right. Last chance to ask a question. I'm going to erase all this, and we're going to do another problem in chapter 2. Here we go. Are you ready? Say goodbye to that. Okay, now this is problem F22. Come on now, right. Fundamental problem F, chapter 2. It's F22. Okay. Force P causes the rod, rigid arm ABC to rotate clockwise about the pin through an angle of 0.02. Okay. Determine the normal strain in the wires. All right, well here, let me try to draw this now. We have a rod. Okay. And it's got a smooth pin here. And there's a wire attached here and a longer wire here. This wire is 600 millimeters. This wire is 400 millimeters. And we'll label all this stuff D, B, A, C, E. And these are 600 millimeters and 600 millimeters. Okay. And they've got a force here. They don't tell us what the force is. They just tell us there's a force there. And it causes the rod to sort of sag a little bit. Let me read it here. It rotates, but not much, 0.02 degrees. That's hardly anything. Well, here, I'm going to try to draw it, though, so that you'll get the idea. See, I'm going to exaggerate. It's impossible for me to draw a 0.02 degree. But I tried to draw that with my red pencil here. And they said that angle there, that tiny little angle there is 0.02 degrees. 0.02 degrees. That show up on the thing there? I'm having trouble with these. I need to get a new pen, I think. 0.02 degrees. Here, let me find a new pen here. My IT person gave me some pens. Try this one. Now, what do they want us to do? Let me read this. It rotates, find the normal strain in BD and CE. Okay. Well, we can find this distance here using the, what do they call that? The arc length equation. Hey, this writes better. Look at here. Arc length equation. Yeah, the way it goes is S equals R theta, but there's a catch. That theta has to be in radians. Here, let's convert this to radians. I'm going to do it. I want you to do it. Convert that 0.02 degrees into radians. Here goes. Okay, I got radians. I got 0.01745 blah 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 radians. Now, does anybody need help with that? Here's your chance. If you don't understand, you're okay with that? And let me ask one of my wonderful students. How about my friend Mohammed? Mohammed, are you okay with that on the radians?
Yes, sir, I'm good on that.
Yeah, I know you are. I know you're good on that. Okay, well, look, we know what this theta is in radians then, see? It's got to be in radians. And you multiply by R. Well, R is, well, it'd be 1200, wouldn't it? So this little tiny distance here, I don't know what to call it. S is a good name. That little tiny distance S is 1200 millimeters times 0.017 blah, 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 blah radians. Okay. I'm going to do that, and I'm going to find how far that goes down. Okay, here goes. Times 1200. Gee, I got quite a bit. I got 20.944 millimeters. Okay. All right. That's
Professor,
I'm sorry, what?
I didn't get that for my radians. I got something different.
Let me do it. Hang on a minute. I'm going to do it over. I appreciate you speaking up. Now, who am I talking to?
Ashley?
Ashley, I didn't get this. Something bad happened. This time, Ashley, I'm getting I get a different answer every time I do this. I'm getting point 0.00349 ratings. Did you get that, Ashley?
That's what I got.
I bet you're right. Let me do it again. I don't know what I did wrong. Who knows? Let me try it again. Times, what you do is you times it by pi, and then you divide it by 180. And thanks to Ashley now, give her a nice big thank you point up there. I appreciate your help. We have the right answer. So let me put the right answer in here. I've got I depend on you guys to check me here. Between us, we can do any of these problems between us. Okay, now we're going to get, this was wrong, see? What I had here is wrong, but we're going to get it right now. Here it goes.
What are we calculating right now? What is that? That's
Somebody said something, but I couldn't quite make it out.
just wondering what we're calculating right now exactly.
Can you say that a little louder, please?
Just wondering what are we calculating right now exactly?
Oh, what we're calculating right now, and who am I talking to?
Brendan.
Brendan, thank you, Brendan. We're calculating how far down the end of this rod went.
Gotcha.
Thank you, Brendan. Is it Brendan or it's Brendan, isn't it?
Yes, sir. Brendan. Yep.
Brendan, got it. Okay. Well, we found out it's not much. It's 0.4189 millimeters, right? See, what they wanted was the normal strain. It's that little Greek letter epsilon in, what's the name of this? This is point C. In the normal strain in CE. That's what they wanted. Well, what it is the 0.4189. Well, actually, it's 887, whatever, and millimeters divided by the 600 millimeters. That's how you get the strain. Okay. Now we're going to get the strain in this wire CE. Here we go. Take that and divide by 600. I got 0.000698 something. Nothing's. See, strain doesn't have any dimensions. It doesn't have units. Well, let's see how we did. I'm going to look up the answer to that. That's F. We did F2. Which problem did we do? Yeah, F22. There we go. Let me go back here and see what they said. They said F22 is, what are we finding, CE? They said it's 0.0698. Is that what we got? Oh, wait a minute. Auga. No, they got another zero there. I think we're okay. This is what they said. 0.00069. Yeah, that's what we got. Yay. We did good on that. Now let's get the other one. How are we doing on time? Oh, we got 5 minutes left. We're doing great. They wanted the strain in a BD. Here, let's write it over here. They wanted the strain in BD. We see what they want here is this little distance that it goes down. Well, you use the same thing. You use the arc. This is called the arc length formula. I want you to be acquainted with the arc length formula. Actually, did you know the arc length formula is the definition of what radians are? See, radians, by definition, are your arc length divided by your radius in a circle. That's the definition of what a radian is. Okay, now, that distance there is going to be 600 times that same angle. We got the same angle, so we're going to go 600 millimeters times that same angle. I'm too lazy to write it. It's right here. That angle hasn't changed any. The angle over here and the angle here is the same. And then you divide, in this case, by the 400 millimeters. Okay, plug that in your calculator. Here's your angle theta. This is it right here. And let's see what the strain, they call that the normal strain. That's the name of it. All right, I'm going to do it. Well, I got an answer. I'm getting, I need some room here to write it. I'm getting the normal strain of that wire BD is 0.0005235. Is that what you got? I'm going to see what they got. I'm going to look at the answer book now and see what they got. This was fundamental problem 2.2. And they said, here's what they said. They said 0.524 times 10 to the minus 3. Now, is that the same thing as what I said? I think it is. Yeah, it's the same. They got the same answer we did. Now, what are the units? Well, strain doesn't have any units. Okay, well, that's our fun lesson for today. I hope you enjoyed it. And next week, you're going to have your test. And I told you about the homework at the beginning of the hour there. Do you have, I'm going to sign off now. Does anyone have any last words, comments, questions? It's your turn. What do you think? Took us a while to get the audio fixed. Well, okay. Enjoy your homework there. And see, next week we're going to be we'll be starting in on the exciting world of properties, material properties. Like I hinted at yield strength. Steel has a yield strength and it'll give at a certain stress. Yeah, we're going to learn about that. Okay, I'm going to sign off. If you have anything to say, now's the time. Okay, well, bye-bye for now.
Goodbye. Thank you very
Bye.
much.
Have a
Thank
good
you so
one.
much.
Thank you.